Hi, I'm Kevin. Welcome to my cave. In the last episode, we started looking at a current mirror, a circuit that can be used to create an equal and opposite current to the current flowing into it. We created a two-transistor circuit that functions as a mirror, and we tested it out. We found that the results were a little disappointing. The current was still dependent on the output voltage because of the early effect. It turns out that I inadvertently lied to you near the end of the last video. Looking at the current versus voltage curves, I found an output voltage where the output current of the mirror appeared to be equal to the input current. I had a wiring error on the breadboard, where I mistakenly connected the op-amp that was monitoring the output voltage of the mirror to the wrong side of the current sense resistor. That gave me just enough of a current-dependent voltage drop that I thought I had a point where the output current equaled the input current. But when I replot with the circuit wired correctly, the output current is always greater than the input, and that gets worse with increasing collector voltage. Well, I was planning anyway to devote this episode to discussing how to flatten these curves. When we had circuits in earlier episodes that had their outputs at a transistor's collector, we were able to get rid of a lot of load dependence by inserting a resistor in the emitter lead. Let's see what might happen if we take our initial current mirror and add emitter resistors to both transistors. In this configuration, we can think of the early effect as raising the base emitter voltage of one of the transistors when its collector voltage rises. So the base emitter voltages won't be quite equal. That's pretty much the same thing as saying that the collector current rises with the collector voltage, since the base emitter voltage still controls the collector current. The transistor bases are tied together, so they have to be at the same potential. In transistor Q1, the base voltage has to be the supply voltage plus the voltage drop across the emitter resistor, plus the base emitter voltage of the transistor. And of course, the base voltage on the second transistor is the same as it is on the first. After all, they're wired together. There's a similar equation governing the base voltage of the second transistor. The only difference is that we use the emitter current and base emitter voltage at the second transistor. Let's combine these two equations. Then we can subtract the power supply voltage from both sides. Next, we rearrange the terms to put the difference between the two base emitter voltages by itself on the right-hand side. Dividing both sides by the value of the emitter resistors gives us an equation for the difference between the two emitter currents. Ordinarily, we want to express this difference as a fractional or percentage imbalance, so we divide by the left-hand current and take the absolute value. Now that we have a nice equation, let's simplify the symbols. Let delta V be the difference between the base emitter voltages, and delta I over I be the fractional error we want to minimize. To choose a value for the emitter resistors, figure out the smallest current you're designing for, the amount of imbalance you're willing to tolerate, and how much base emitter voltage difference you expect. 3 millivolts is a pretty typical value to use. 10 millivolts is conservative. Don't go crazy with the resistor, though. It will limit how much current your circuit can handle. Let's make this modification to our breadboard circuit and give it a go. I'll use the 3 millivolt value for voltage difference and assume a current of at least 200 microamps. I want the imbalance to contribute no more than 1% to the output current. That gives me a value of 1.5K for the two resistors. We'll try that. That will make our mirror look like this. Here it is on the breadboard. The significant change from what we saw in the last episode is the addition of the two emitter resistors. If you define significant as not embarrassing, Kevin, that is. But enough said about that. Let's plot the curves for this one also. If you recall from last time, when we plotted the results for the simple mirror, we saw that the output current was not uniform, but increased with the collector to emitter voltage. In addition, when we fixed the wiring mistake, we found that the output current is too high at all voltages. Have we now managed to improve things? Well, when we plot out the results for this circuit, we see that the currents are almost perfectly flat, we've cured the collector voltage dependency. The output currents are now a few percent lower than the input currents. We expected that because the input, in addition to supplying the reference current, is supplying the base current for both transistors in the mirror. It's conceivable that we might want tighter control than that. But what's more significant is that we've limited the current range that the circuit will support. If we go to less current than the minimum we designed for, then the emitter resistors will be too small, and the early effect will put in another appearance. We see that if we blow up just the plot of the 100 microamp test. There's a slight dependence of the output current on the output voltage, and that will only get worse at the lower currents. And of course the emitter resistors will limit the amount of current that we can source at the high end. If we tried to pull 20 milliamps off the circuit, we'd need a 30-volt output voltage to get it. I have applications where I want 1,000 to 1 or greater range in currents. This mirror isn't going to work for those. Before I go on to describing how to fix the current range, though, I want to mention quickly another idea from the brilliant analog designer Bob Widlar. His idea is to use the emitter resistors, but give them unequal values. If we do this, we'll get an output current that is approximately the input current times the ratio of the resistor values. There are some more calculations that you have to do to compensate for the fact that we've now added an imbalance in the emitter voltages, but at this point you probably have the tools to figure that part out. One important thing here is that we can sometimes use this trick to compensate for imbalances in our circuit by trimming one of the resistors. Let me demonstrate the Widlar current mirror on the breadboard. By replacing the 1.5K resistor on the reference transistor with a 3K one. I ran the curves off camera, and here's the result. On this setup, the output current, which should be approximately double the input current, is about 8% low. That's good enough for some purposes, and the ratio could be adjusted easily by trimming one of the resistors. Now let's move on to broadening the range of output currents that our circuit can handle. In the electronics folklore, the story goes that Barrie Gilbert and George Wilson challenged each other to solve the problem overnight, using no more than a third transistor. Wilson won the challenge and invented the current mirror that now bears his name. The Wilson mirror begins with the same pair of transistors as the simple mirror, with their emitters tied to a supply rail. But the pair is the other way around, with the diode-connected transistor now on the right-hand side. And we add a third transistor on the right-hand side, with its base connected to the input port. The input and output currents are connected to the base and collector of this new transistor. This circuit looks weird at first, but it too functions as a mirror. Let's quickly walk through it to see what's happening. To begin with, we can see that the bases of Q1 and Q2 are the same voltage, one diode drop from the power rail. The base of Q3 and the collector of Q1 must be a diode drop beyond to that. Now let's think about the currents. The base voltages of Q1 and Q2 are equal. Their collector voltages differ by only a diode drop, so the early effect should be minimal. That means that their base currents should also be nearly equal. Call that current I sub B. Their collector currents should also be nearly equal, because we're assuming the transistor characteristics are the same. Both base currents feed into Q3's emitter, together with one of the collector currents. Q3's base current is going to be that current divided by Q3's beta. We can mostly ignore the contribution of the base currents. 2 divided by beta squared will be a tiny number. So we can think in terms that one base current is associated with the programming port, giving it a total current of I sub C plus I sub B, while the other base current remains flowing through the collector of Q3, giving it also a total current of I sub C plus I sub B. I'll leave it to you to verify that there's negative feedback operating so that perturbations of the voltages or currents return back to this state. If you're really curious, you can also verify that the circuit wouldn't work the same way if we had left Q1 as the diode-connected transistor. What Q3 is doing is absolutely brilliant. It's suppressing the early effect by holding Q2's collector at a nearly constant voltage. In this role, Q2 and Q3 form a circuit called a cascode, which has other advantages as well, that I'll get to later in this series. But Q3 also has the effect of taking the combined base currents from Q1 and Q2 and splitting them apart again, routing one to the programming port and the other to the output port. This gets rid of the current imbalance of the simple mirror. I hope that whatever bet Gilbert had with Wilson that he paid off handsomely, since this mirror appears in the internal circuitry of almost every analog IC out there. Let's build this circuit and check it out. The schematic change is pretty simple. I just add an external PNP transistor to the matched pair I was using. In the breadboarded circuit, you can see the extra transistor just to the right of the matched pair. I'll test it out off camera. The results have the same general shape as what we had before, but without the current handling limitations. I'm getting about 4% discrepancy between input and output currents. That's not horrible. Some of the remaining imbalance comes from the fact that the collector of Q2 is still at a diode drop away from the collector of Q1. This is easy enough to correct. We can add another transistor, connected as a diode, to introduce another diode drop, bringing Q1's collector to the same voltage as Q2's. This configuration is called a Symmetric Wilson mirror. You can see how the two transistor pairs are mirror images of one another. Let's make this modification and see if it helps. Once again, the schematic change is pretty simple. I'll use the second matched pair for the two transistors. In the breadboarded circuit, you can see the second pair off to the right of the first one. Once again, I'll run the data collection off camera. Well, that resulted in some improvement, although it's getting hard to see in the graph. The systematic error has been knocked down from about 4% to about 3%. But now I'm a little more stuck about how to improve, and a lot of what remains would require some redesign. The first error that I want to examine is coming from the current source. The meter is measuring the current at the emitter of the transistor, not at the collector. That will make it read too high by a factor of beta plus 1 over beta. If we assume that the transistor's current gain is about 100, that's a third of the remaining error right there. Of course, we could fix that by using an instrumentation amplifier the way we did on the output side. But we also have to consider the effect of component precision. The current sensing resistor is a cheap 1% resistor, so we could be reading an additional 1% higher low on the source current. And that resistor isn't the only one that's critical to the measurement. The output current measurement will depend on both the current sensing resistor on the output lead and the gain setting resistor on the instrumentation amp. Both of these resistors are also cheap 1% resistors. And of course, all three resistor errors might accumulate if we're unlucky. But perhaps the most significant error is coming from the transistor pairs themselves. The datasheet for the DMMT5401 pair that I'm using promises only a 2% match in both beta and base emitter drop. That's saying to me that the measurements we're getting are already better than we deserve with two transistor pairs of this type. There are better pairs out there. It used to be that the gold standard in the synthesizer world were the LM394 and LM395 NPN and PNP pairs. But they were discontinued some time ago. Similar parts like the SSM2212 and SSM2220 or the MAT02 and MAT03 are also on their last legs, if not outright discontinued. These chips are either unreasonably expensive, available only from sketchy suppliers, or both. The best alternative for well-matched pairs appears to be the AS194, AS394, and AS395 from Alpha Semiconductor in Latvia. I'll admit that I haven't tried them, although I found a few distributors that source them. Frankly, in today's political climate in the United States, I'm kind of reluctant to do any design that depends on a sole source that's a Russian-owned company in one of the Baltic states. There are some other choices, some of which appear to still be being made. I've thrown up a few part numbers on the screen that you might be able to find, but I've not made a lot of effort to source precise match pairs. Instead, most of what you're going to see on this channel moving forward will either be designed to be robust in the face of this much error, trim the errors out, or use ICs that incorporate current mirrors as part of their internal design. In fact, I might have skipped over current mirrors altogether, except that they were important for understanding the capabilities and limitations of our analog ICs. So, in the next episode on the channel, I'm planning to get back to the oscillator design that we've had on hold for a while, and let it have a single frequency control by replacing one of its current sources with a mirror. I hope you'll stay tuned for that. I'm also looking at starting another series going over op-amp basics, because I've seen a few viewer questions that suggest at least some viewers need to learn more about the bread and butter op-amp circuits that most of our design use. I hope these ideas are interesting enough that you might favor me with a subscription. In the meantime, stay safe, stay healthy, stay curious, and take care of one another. Bye.